Welcome, everyone. My name is Stephan Mandt, and I'm with UC Irvine. And together with Karen Ulrich from Meta Research and Yibo Yang from UC Irvine, I will present on data compression with machine learning. In this tutorial, we will begin by providing a high-level introduction to neural data compression. In part 2, Karen will talk about using machine learning for lossless compression. And in part 3, Yibo will talk about lossy compression with machine learning. And towards the end, I will point to relevant resources and open problems. So let's begin part 1 of the tutorial. I will first provide a motivation and overview of the topic, and afterwards I will review basic concepts of lossless and lossy data compression. Finally, I will draw a connection between compression and generative modeling. So let me start by reviewing some background information on compression. As we produce more and more data every year, we experience challenges in storing and transmitting this information. On the one hand, we have new application areas, for example, video streaming, healthcare data, data arising in edge computing, and decentralized machine learning. And all of these applications involve massive storage and communication costs. On the other hand, we face new types of data, for example, LiDAR data, VR content, MRI data, multi-view video, or climate and genomic data. And for many of these examples, there's currently no established compression algorithm available. Now, at the same time, we're faced with serious environmental and resource concerns, because most of the data will be stored centrally somewhere in a data center. And those data centers are responsible for about 1% of our global energy consumption. And furthermore, the internet is dominated by video streaming, so even modest improvements in increasing video compression performance would lead to enormous bandwidth savings. So let me provide a couple of examples. And to start with, let's take a closer look at video transmission and streaming. Now, there's a lot of generic video content on the web, but there's also a fair bit amount of specialized content, for example, sports television or video conferencing. And now training specialized neural codecs on such low entropy content should in principle lead to sizable compression gains. And in fact, two independent research groups have shown impressive amounts of bandwidth reduction were possible, in particular for video conferencing data. As an example of a new type of data, consider LiDAR. LiDARs measure distances to objects by targeting them with a laser and produce three-dimensional point clouds. And the picture here shows, for example, a recent LiDAR neural compression approach applied in the context of self-driving cars. Now, typical LiDAR data sets contain up to billions or tens of billions of data points that all need to be stored and compressed. There's also a growing amount of genomic data, and there's a growing need to find new compression algorithms for those. And at this point, the size of a fully sequenced genome is about 10 to 100 gigabytes. And as medicine advances, we may want to do this millions, if not billions of times, sequencing every human. And in fact, not only once, but possibly repeatedly, because genomes may differ in various cells in the body. So all of this together easily requires exabytes of available storage. And finally, consider the growing amount of AR and VR content. Depending on the application, we may need to compress two-dimensional videos or three-dimensional scenes. And in general, transmitting VR content is fairly challenging and more challenging than normal video. But it turns out that there are also new ways in which we can compress VR content that weren't possible before. For example, we can take into account how people interact with virtual environments. Data transmission involves two types of coding schemes, source coding and channel coding. And it's best to understand them jointly as a pipeline from a sender to a receiver. In source coding or data compression, we convert data into short binary strings, and we then transmit these bit strings through a low bandwidth channel. Now, this channel may be noisy, which means that it may randomly corrupt our bit string. And to combat this, we'll need to transmit our bit string with some redundancy using a technique called channel coding. Now, in this tutorial, we will not deal with channel coding and consider it a solved problem. And instead, we will focus on the data compression problem alone, assuming that we have a noise-free channel. Now, compression-related ideas have influenced machine learning and the sciences for quite a while. For example, the notion of Occam's razor, which states that simple theories should be preferred over more complex ones, goes back to the Middle Ages and has been formalized into a mathematical framework in the 1960s. And other examples include regularization, the minimal description length principle, clustering, the information bottleneck principle, and so on. And furthermore, compression models, methods are actually already being used in machine learning. For example, in sketching and streaming algorithms, in gradient compression for federated learning, and also in model compression or neural network compression. But in this tutorial, we will focus on machine learning for compression, taking into account that statistical modeling has been key to traditional compression for quite a while now. For example, well-established algorithms such as Lempel-Ziff estimate an autoregressive model of the data on the fly. There's also a growing amount of research on incorporating deep learning into traditional compression pipelines. And while these are important developments, they're not the focus of this tutorial. Instead, we will focus on neural compression. And by neural, we refer to approaches that involve deep learning, generative modeling, and related techniques. We also focus on approaches that are learned end-to-end based on unlabeled data. And we will discuss the many advantages of these approaches. For example, achieving better reconstruction qualities than classical codecs at the same or smaller file sizes, the possibility to adapt neural codecs to specific data modalities and instances, and also our ability to optimize neural codecs for perceptual quality or other objectives of interest. Next, I will present an overview of lossless and lossy compression. And to begin with, let me compare both approaches on a high level. In lossless compression, we represent discrete observations by binary code words. And the idea is to represent frequent observations by short code words and rare observations by longer code words, using a probability model of the data. And in fact, Morse coding is roughly designed like that, following this principle for letters in the alphabet. Lossless compression allows for perfect data reconstruction by definition, and its use cases are medical images, text, and other forms of symbolic data. Now, it turns out that lossless compression isn't always necessary or even possible. And for example, we cannot compress real-valued signals losslessly. Now, in lossy compression, we are willing to trade some information loss for a much smaller file size. And we thereby try to keep only relevant information, which we will discuss in later parts of this tutorial. We will also see that lossy compression involves lossless compression oftentimes as part of the pipeline. And use cases here are image and video compression, as well as most types of visual or sensory data. So let's discuss lossless compression in a bit more detail. A code is a mapping from observations to binary bit strings, and we will denote the encoded data as code words. The goal of compression is to find not only an arbitrary code, but a code that minimizes the expected code word length. And there's a particular type of code called entropy code. And this type requires a probability model queue of the data and has a further defining principle, namely that the expected code word length is approximately the estimated negative log probability of the observation under consideration. And since the expected log probability of a distribution is its entropy, The expected code word length of an entropy code can never be shorter than the data entropy. And in fact, a practical code can at best realize the cross entropy between the data distribution and the code's probability model. Now, the idea of neural lossless compression is as follows. We will use generative models to learn this distribution Q from data, and we will hope that entropy coding will then do the rest for us. In the simplest case, Q is a tractable likelihood model, where we would have direct access to the log probabilities, but we will learn from Karen in part 2 that entropy coding with latent variable models is also possible. And furthermore, if our model is a continuous density, we will learn how to quantize it to discrete also in part 2. Now here's how lossless compression might look like in practice. Let's assume that we have discrete observations A, B, and C living on a grid. And these could be images with discrete RGB values. Now, to compute every observation's probability, we need a probability model over the lattice points, here shown in green. And as the plot suggests, this model could have been obtained by discretizing a learned continuous distribution. And with the help of the model, we can estimate every observation's negative log probability. And these log probabilities, along with the observations, are then fed into an entropy coder that converts them into short binary strings. And importantly, the data points can be uniquely recovered from that bit string. To make entropy coding a little less abstract, I want to explain it based on the popular so-called arithmetic coding technique. And to this end, consider the following probability distribution over 10 possible events. And the first thing we do is we compute upper and lower cumulative probabilities, here shown in dashed and solid orange. Now, to encode an observation, here 7, we would then look up its upper and lower cumulative probabilities. And those values define a subinterval of the interval 0 and 1. And every number in this interval uniquely characterizes the observation. However, just picking an arbitrary number would not lead to compression. And we therefore pick the real valued number, which has the shortest binary representation so that it is still contained in the interval, which would be 0.111, or 7 divided by 8. Now, it is evident that the larger the probability of every observation, the fewer bits we will need to find such a representative number. Now, practical lossy compression also draws on lossless compression. However, this approach usually also involves a lossy quantization step, shown on the left. Now, the figure here introduces quantization as a form of rounding to an integer grid, but note that there are also other types of quantization which we will discuss in part 3. Currently, the predominant lossy compression paradigm is called transform coding, thanks to its computational efficiency. And transform coding involves an additional transformation step. So instead of quantizing the data in its original space, we first transform the data into a latent space using a mapping F. This mapping could be just a discrete cosine transform or a nonlinear mapping induced by a neural network. And with the help of an inverse mapping G, we can approximately reconstruct the data in the original space. Now, in this context, we often like to denote data in the original space with the letter X, and we will call the space in which we quantize the data as latent space and call the corresponding variables by Z. The reconstructed data, which we obtain by applying the encoding and decoding transforms along with quantization, will then be denoted by X hat. Now, one example of a transform code is JPEG. In this example, the encoding and decoding transforms are as follows. We first map RGB channels to so-called YCC components. And it turns out this is just a linear transformation where one component encodes the overall brightness level and the other two components encode color differences. Now, second, we perform a discrete cosine transformation on the data. And finally, one scales up the corresponding values and discretizes them by rounding. Now, the encoder transform, F, is just a composition of these three linear operations followed by rounding. And the decoder transform is obtained by applying the inverse matrix multiplications to the latent state Z. And since all of these mappings are linear, this is just a linear autoencoder. So we have reasons to believe that we can come up with an even more powerful coding scheme by introducing nonlinearities. Now, finally, let's discuss how to evaluate lossy compression. Often we'll plot the performance of a lossy compression algorithm or a lossy codec as a so-called rate-distortion curve. And an example of that is shown on the left-hand side. So note that this involves two quantities, the rate, which indicates the average file size, and the distortion, which measures how much the original data and the reconstructions of images differ. For example, this could be a pixel-wise mean squared error, and ultimately we average this quantity over many images and their corresponding reconstructions. We can now evaluate these two quantities for any lossy codec and plot them on the plane. And every parameter setting will result in a point, and multiple settings together will span a curve. Now, when comparing different algorithms, each one will have a different rate distortion curve. And the best compression performance, or the best algorithm, will ultimately show both a small rate and a small distortion. And the extent to which this is possible will be discussed by Yibo in part 3. Now, finally, I would like to draw on connections between data compression and generative modeling. To better understand this connection, let's look at generative models and let's revisit what happens when we sample from the model. So generative models usually start from a random vector, which could be, for example, uniform or Gaussian distributed. And in a sequence of operations, which we denote here by G, they will transform this random vector into a data sample. And we can interpret this operation as a decoding step. And interestingly, we can also generate data with compression algorithms. For example, when we decode a uniform sample over the interval 0 and 1 using arithmetic coding, this will result in a draw from the approximated data distribution. We can now compare classical and neural compression algorithms visually by decoding random bit strings, which is shown here. And JPEG, shown on the left, shows artifacts of run length encoding and cosine features discussed before. And for comparison, a more recent neural compression model on the right will produce typically smoother and more naturalistic local textures. Now let's consider a specific generative model in more detail. A latent variable model is characterized by a joint distribution over data X and latent variable Z that factorizes into a likelihood and a prior. We will also consider a conditional distribution Q of Z given X that is sometimes called variational distribution and sometimes called encoder, depending on the context. The marginal likelihood, log P of X, is intractable to compute for latent variable models, but we can invoke Jensen's inequality to derive a tractable lower bound, which we also called elbow. A specific deep latent variable model is the variational autoencoder, or VAE. And VAEs parameterize both encoders and decoders by neural networks. We can now compress data by sending X through the stochastic encoder and round the resulting most likely encoding to the nearest integer vector. We then can compress the discrete latent variable Z by entropy coding it under the prior. And for reconstruction, we can send Z through the stochastic decoder and again use the most likely decoding. And in fact, this is just another example of nonlinear transform coding. For lossy compression, there is some information loss since we can only recover the original data point up to a reconstruction error. But we can also do lossless compression. And in this case, we can use P of x given z to also compress the residual error. And interestingly, it is possible to get certain bits back that were spent on compressing z, which is what Karen will discuss in part 2. Now, we may ask if GANs are also useful in compression. And it turns out that we will still need a latent variable model, but we can use adversarial training to enhance its performance. Now, as Yibo will explain in more detail, achieving low distortion is not always the same as achieving good perceptual quality. And even variational autoencoder-based codecs can still suffer from compression artifacts such as blurriness. Now, to enhance their perceptual performance, we can add a discriminator loss function that compares the decoded images with ground truth data. And this setup is similar to VAE GAN hybrid models that have been proposed in the generative modeling community in the past few years. Now, Hi-Fi-C is a popular example of this for image compression, and it's illustrated on the image on the right-hand side, where we compare relative to JPEG. If we focus on the left half of the image, you'll see that the reconstructions are relatively sharp and contain very few compression artifacts, whereas the right half was compressed with JPEG at twice the bitrate, and it actually shows more artifacts of that compression scheme. So we will hear more details about this line of research in part 3. Now, it turns out that our focus on latent variable models for compression is no coincidence. Lossy compression, when done by first principles, will actually always result in a variational autoencoder. To understand this, it is useful to think of the standard lossy compression pipeline as a Markov chain, where an encoder sends data x to a discrete latent variable z for entropy coding, and a decoder maps the latent state z to a set of reconstruction points x hat. Now, in this approach, the first goal is to minimize the entropy in the latent space, because this is where we would like to losslessly compress the z variables. The second goal then is to reduce the level of distortion. Now, goal 1 is just lossless compression in the latent space. Note that we can achieve it by learning an entropy model, P of z, in the latent space, and then use it to approximate the distribution of encodings, Q star of z, by minimizing the cross entropy objective. Now, the resulting objective is a weighted combination of cross entropy on the left and reconstruction error on the right, which almost already looks like an elbow. But we can make this connection even more precise. And to this end, let's assume that the encoder is a conditional distribution, Q of z given x. And let's, for now, consider the decoder D to be deterministic. In this case, Q star is the so-called aggregate posterior, which expresses the distribution of the encoded data in latent space. We can furthermore interpret our entropy model P of z as a Bayesian prior. And finally, the distortion term becomes an expected log likelihood if we pick a likelihood function whose logarithm corresponds to the distortion measure rho. Now, a common choice for the variational distribution Q is a uniform distribution, in which case the analogy becomes exact. And the uniform distribution simulates the rounding operation during training and will lead to a practical codec, as Yibo will explain in more detail in part 3. In summary, we talked about the fundamentals of neural data compression, and we saw many close connections to generative modeling. We started with neural lossless compression and culminated in neural lossy compression in the form of nonlinear transform coding, which is summarized by the plot on the right. Necessary steps here were to encode, quantize, entropy code, and decode the data in an end-to-end trainable fashion. We also discussed basic connections to variational autoencoders and GANs.